Okay, we're going to do a couple of problems here where we're going to compute some Laplace transforms of a couple of different kinds of functions. Remember, again, we've got that table in the back of the book that helps us with Laplace transforms of some basic functions, and we can use those with a couple of our theorems to get Laplace transforms of more complicated functions. So, for example, let's look at number 4 on page 278. On this this particular problem asks you to compute the Laplace transform of t to the 10th e to the negative 7t. So we know what the Laplace transform of t to the 10th is. According to our table, remember that the Laplace transform of t to the n is n factorial over s to the n plus 1. So in this case, our n would be 10, so we could easily compute that particular Laplace transform just by plugging in 10 for n. Now, we've got this e to the negative 7t piece in here. We can also compute, we know that this particular function, when we multiply a function times an e to a negative sa, shifts it by a. It translates it along the s-axis, if you will. So what we can do in this particular problem then is, since we've got e to the negative 7t, we know the Laplace transform of this will be 10 factorial, because we're just going to plug it in for n, and we know we've got an 11th power because of the n plus 1. However, instead of just an s in the denominator, this is going to translate it over 7 units along the s-axis. And remember, in this case, it will be s plus 7, because we're going to do minus a minus 7. So we can get that Laplace transform pretty quickly. Let's see if we can do another one. Let's say you're asked to do let's do number 10 on page 278 as well. We've got the Laplace transform of e to the 3t times 9 minus 4t plus 10 sine of t over 2. We recall that the Laplace transform is linear, meaning that it breaks up over sums and differences, and you can factor out constants. So we know that we can actually do the Laplace transform here piece by piece. We recall that the Laplace transform of 1 is just 1 over s. The Laplace transform of t, of course, using that formula we had above, would be 1 over s squared. And if we have the Laplace transform of sine of kt, that's k over s squared plus k squared. So we can use each of these Laplace transforms to compute the Laplace transforms of the 9, the 4t, and the 10 sine of t over 2. Again, remembering that the Laplace transform is linear, and we can pull out the constant. So this is like 9 times 1, this is 4 times t, this is 10 times sine of t over 2. And also noticing that our k value here is 1/2 for the sine function. And just like in the last problem, we have e to the 3t. We know that 3 is a shift along the s-axis. It's going to shift it right 3 units, or we're going to subtract 3 off the s everywhere we see s in the Laplace transform. So in this particular one, we'll get 9 over s minus 3. Again, the 9 is because the constant pulled out. The Laplace transform of 1 is 1 over s, and we're replacing the s with s minus 3. The next one will be minus 4 over s minus 3 squared. Again, just like before, pull the 4 out. Laplace transform of t is 1 over s squared. Replace the s with s minus 3. For the sine of t, we got a 10 times. Our k again is a half, so we would have a 1/2 over s minus 3 squared plus 1/4. So again, we're using the Laplace transform for the sine. Our k is a half, so that's where the 1/2 and the 1/4 comes from. And again, since we have that e to the 3t out in front, we're going to replace that s with the s minus 3. All right, so that's how we do Laplace transforms when we have a function times e to a power, an at, if you will. So let's do another one where we have a unit step function in here. So again, let's look at one of the ones that's in the same section in 7.3. And let's look at number 40. Let's look at number 40. In number 40, we have the Laplace transform of 3t plus 1 times the unit step function of t minus 1. Remember again, the big theorem we want to use is Laplace transform of unit step function of t minus a, f of t minus a, is e to the negative sa times the Laplace transform of f, not the f of t minus a, but the f of t. Okay, so that's where the capital Fs part is coming in. Okay, so notice in this case we have unit step function of t minus 1. That means I need to write this function here, the one that I'm underlining, as a function of t minus 1 in order to be able to use the theorem. So to that end, if I just put in t minus 1 for t, notice I would have to distribute that 3 over to the minus 1, which really means this is 3t minus 3. I want 3t plus 1. That's what that's equal to. So to keep everything equal, I need to add 4 so that I actually have these are equivalent to one another. And now I have my function of t minus 1 because my unit step function is in terms of t minus 1. When we compute the Laplace transform, however, when we do that, looking at our theorem again, we're going to treat this t minus a like it's the variable and then just use it for the Laplace transform. So in this case, we have 3 times t minus 1. We're going to just think of that as 3t when we do the Laplace transform. So that would be 3 over s squared. And the 4, Laplace transform of that is just 4 over s. To adjust for this unit step function, remember we multiply by e to the negative t in this case, e to the negative s, because our a in this particular case is 1. So that's doing our Laplace transforms when we have multiples of the unit step functions, and also when we just have a translation. So we're basically doing two different types of translations.